So let's have a look at that homework that's coming due. Okay, there's two of them. They take a bit of calculations, so you want to give yourself some time to be working through these. So this first one is 231. This is just a standard biaxial strain kind of problem. So what you're given there is the strains in the x and y directions. Of course, they're not written down for you. You need to figure them out from the sketch. So epsilon xx in the x direction, epsilon yx in the y direction, and gamma xy is the angular shear strain on the lower left-hand corner angle. Okay. So that would be the first thing. This is a lot like doing the biaxial stress stuff, where the first thing that you want to do is to go ahead and write those down. So I would start with that. So I want epsilon x, epsilon y, gamma xy. And then the other thing I would want would be the angle that I'm going to work with. So, those are the things that I would start with. So what's happening there in the x, and what we're doing here, this is a dimension sketch. It's really a schematic is what it is, because you can't really dimension strain, but that's what you do on these sketches. It's just kind of this way that a lot of books use to present it. So the strain in the x is 450, and that's micro. That means 10 to the minus 6. Remember, strain is a dimensionless quantity. So that's getting longer, so that'd be positive. But notice in the y, it's negative, okay? Okay, gamma xy, that angle is getting smaller. Now, if an angle is getting smaller, that means it's positive shear strain. And then the one thing that's different from strain to stress is that you measure from the horizontal. So what we got there is a counterclockwise 73, so that would be a positive 73. So there are the values that you'd be plugging into the equations. Okay? So you'd start with that. So we good with that? And from there, it's just a matter of plugging into the biaxial equations. So, you just go ahead and do that. So you got epsilon x1 is epsilon x plus epsilon y over 2 plus epsilon x minus epsilon y over 2 cosine 2 theta plus gamma xy over 2 sine 2 theta. So you just plug everything in. The first angle that you would use would be 73 degrees. So what I'm doing there is I'm taking 2 times 73 degrees. And that would be 146 degrees. So that's where that 146 that I'm plugging in comes from. And when I run those numbers, I get the strain that would occur in the x1 direction. Okay, it's 99 times 10 to the minus 6. Just like with the stress, I don't put I just run the numbers. I don't put the units in there. I don't even put the micro in there until I get to the end. It just gets too cluttered for me if I do, so I don't bother with that. Okay, so that's, you might call it theta x1. Then we also have theta y1, which is the strain that would occur on this line right there. So that would be 90 degrees more than 73. So I'll go ahead and run the equation a second time using twice 163 degrees to plug in. Okay. So this has another similarity here with the biaxial stuff, and that you're just plugging into a big equation and running the numbers. The challenge is more kind of understanding what it means in my mind. Okay. So we'll look at that here in just a minute. Okay. All right. So then you just plug it in again, and you'll get 261. So this is using this angle here this time, okay? So that's the angle that you would plug in. Now, remember to double it, of course, because the formula is 2 theta, so just double it, okay? And so you'll get 261 the second time. Now, you can use the shortcut formula if you like. Just like with stress, there's a shortcut formula, so you can use that. So you just plug the numbers into the equations and you get the strains at the different angles. Again, though, one of the big differences here between stress and strain is the reference angle is the horizontal. So you're going counterclockwise from the horizontal. Okay. All right, and then you've got gamma x1, y1. There's the equation. You're going to use 73 degrees to plug into that, and when you do it, you should get a negative 725 times 10 to the minus 6. Okay. All right. So those are the numbers that you get, and then from there, I would like you to make a sketch. Now, there's all different ways of sketching this stuff. I mean, I do it 3 different ways. We did it with a rectangle to start with, where we looked at how a rectangular plate would deform. We'll look at one with a circle here, maybe on Monday. And then this style here, which is kind of what comes out of the textbooks, this is really more schematic than anything. It's not a perfectly dimension type realistic sketch. It's more just a sketch to show the dimensions. It's got a couple of funny things about it, okay? So the sketch I would come up with would be something like that. So in the x1 direction, it's getting longer, okay? So epsilon x1 is equal to 98.8 times 10 to the minus 6. Okay, so that's going that way. Now epsilon y1 is coming back that way, so that's epsilon y1. Okay, and that's equal to negative 261 times 10 to the minus 6. So that's why that's getting shorter. And so one odd thing about this style of sketching is you're showing strains as though they're deformations. They're not, but you have to take a strain times a length to get an actual deformation. So that is one kind of odd thing about this. The other odd thing is that you show all of the shear strain on one side, because the convention on this, and again, these are schematics, and by schematics I mean they're not perfect representations. They're just drawings that are made for some purpose so that everyone agrees on how to write them to show certain information. So people just agree on how they are to be drawn up. So you've got a certain reference angle here. You hold that line, and so it doesn't move at all, and you put all the strain on one side, and the only reason you do that is it allows you to dimension it in one location. Okay. So that strain in that lower left-hand angle when you curve up is 725. It's negative. When we ran the numbers, it came out to be negative, so that means the angle gets bigger. Okay, so that's why that angle is increasing. So we're doing all right with that? Okay. So you do have to kind of learn that strain convention for how to make the sketches. It's just that. It's just a convention. So that's the first one there. The same thing as biaxial stress. I do think the stress stuff is more important because stresses will actually cause something to fail or something you pay an awful lot of attention to. Strains are a little more about deformation, which may not be important depending on what you're doing. Okay. All right, 234 is kind of a long problem, but it's worthwhile to kind of understand it. What you want to do, you're given the stresses that act on this plate. You're also given the fact that you've got a line from A to B that's 3 centimeters long and makes a 28-degree angle with the horizontal. So you have to go through this series of steps to get to the new length of the line, because what we want to know is if we have that 3 centimeter line from A to B on that plate when there's no load on it, then we stress it as shown. How long is it going to be? All right? So the steps are to start with the stresses and the material properties, use Hooke's law, get to the strains, then use the biaxial strain equations and get to the strain at 28 degrees. And then once you've got that, find the new length. That's the steps. So it's kind of important to see that. A lot of number crunching on this, but that's I think the important thing is just that flow chart, that you understand, what's going on there. It's, again, by the time you're a second-year engineering student, I don't think plugging the numbers in is, should be that challenging anymore. It should be more about understanding the equations and how they're put together and how the relationships work to get from one step to the other. Okay. All right, so that's kind of the flow chart. So that's really what I want you to understand, is you use Hooke's law to get from stress to strain. The strain is really kind of related to deformation. But now you've got the strain at an angle for AB, so you've got to use the biaxial strain equations to get to that. And then after you've done that, you want to find the new length using the strain, okay? All right, so there's Hooke's law. So epsilon x is just 1 over e sigma x minus nu sigma y. So that gets you epsilon x. It's negative, a little less than 1%. So negative 0.007833. So that line in the x direction, that edge, I guess I should say, will get shorter by 0.7833%. Okay. So if it was originally 100 millimeters long, it'll now be, what, 99.2167 or something like that. It'll be shorter. Or I'm sorry, 99 point, or whatever the heck, 99.2167, I think. Okay, something like that, okay? So we find the strain in the x direction. Okay. All right. Now once we got that, we want to find the strain in the y direction next. And yeah, it's just another formula. It's the same basic formula, it's just for y instead of x. So instead of epsilon x, you got epsilon y, and you switch sigma x and y. So you just do the same thing again. You'll get epsilon y, that's 0.0035. So in the y direction, the edge of the plate will get 0.35% longer. So if it's originally 100 millimeters long, it'll now be 100.35 millimeters long. So what's happening when you apply those stresses is that plate will form. And the amount of deformation will depend on the material properties, of course, and the stresses applied. So we get to that. All right, we want to find the shear also, because we got shear stress applied. Looks like a negative shear stress. So that'll get you a shear strain of negative 0.004. So now once you've got that, you've got epsilon x, epsilon y, gamma xy, you can plug everything into that equation. You're going to use a 28-degree angle there because the angles are measured from the horizontal. And you're going to find the strain at 28 degrees, which is a combination of epsilon x, epsilon y, and gamma xy in the angle. Okay, and that comes out to be negative 0.00699. So that line AB will get shorter by 0.699%. So it's not going to be 3 centimeters long anymore. It's going to be different. And that's actually the basis of some of the strain gauges they use. They put resistors, I think. They kind of attach them to the material. And when the material strains, the resistors change length, and that changes their properties. So when you're running a little bit of current through them, you get different values output. So by reading those output values, I think that's the basis of a strain gauge, I think. Okay. All right. So we run that equation, we get the strain, and then once we know the strain at that 28-degree angle, we can figure out, the 1 plus epsilon times the original length to get you the final length, so it's 2.979. Okay. All right, now, let's see. I do want to point out also why there's that difference in convention. Okay, stress starts at the vertical plane. So this is the convention for stress. So if you're going to then go to the, let's see, I'm just trying to think how to express this. Okay, let's say we're going to go 28 degrees from this plane. We will get to this plane right here. But the stress acts normal to the plane. So that's sigma x1 for 28 degrees. You all with me there? Okay. Because the stress, by definition, it's normal stress, it's normal to the plane. So in order to have the strain lined up with the primary stress that causes it, the strain is referenced to the horizontal axis, because if you apply that stress to something, what you're going to get for the deformation will be right in line with that stress, okay? So there's the deformation that is most in, okay, at 28 degrees, that would be the strain that affects that line. That is mostly caused by that stress. That's why they use the different reference planes. So that for a given angle, the strain and the primary causative agent of it, which is sigma x1, are in line, okay? Now this is also caused by nu sigma y1, that gets thrown in there too, but the primary causative thing on it is right there. So that's why they use these different reference planes, so that everything will line up. So sigma x1 28 has the same angle as the primary stress that causes it. Not the whole stress, because there's also some sigma y1 going in there too, but the primary cause. Okay, that's why that's done. Okay. All right. Good enough. Enough for 1 week. Bunch of midterms, quizzes, tests, all that. Time to go home. All right. Sounds good to me. So we'll call it good. So that stuff's due Monday. Okay.